The global liquefied natural gas supply chain spans massive offshore platforms, highly pressurized cryogenic engineering, and international pricing indices. To understand how gas moves from wellhead to power plant, we'll translate this physical and economic sequence into a single hand-drawn map. Before we start, clear your desk. Get a blank sheet of paper, a black fine liner pen, and teal, orange, and red markers. We will build this using Tony Buzin's radial mapping technique. He popularized the concept of mind mapping. By placing a central anchor in the middle of the page and radiating branches outward, we use spatial relationships and simple doodles to lock technical data into our working memory. Physically drawing these systems forces you to trace the exact path the gas takes. By the end of this exercise, you will hold a permanent mental model of the entire industry. Step 1. Right in the middle of your page, draw a three-dimensional box. Inside it, write the LNG value chain in bold, all caps. Keep this central box tight. You need to leave at least 4 inches of negative space on all sides to accommodate the 10 radial branches we are about to draw. That box anchors our map. It represents the exact point where upstream thermodynamic physics converts into downstream global economics. This schematic illustrates the first stages of gas processing. Draw your first branch pointing up and left, labeled extract, and a second branch right next to it called sweetening. Add a quick doodle of a gas well. Raw methane-rich gas flows from the field facilities directly into the pipeline reception area. Now locate the block labeled acid gas removal. Here, the raw gas undergoes sweetening. Draw a small cloud on your sweetening branch to represent carbon dioxide and hydrogen sulfide. These impurities must be stripped out completely. If they reach the cryogenic cooling stage, they will freeze into solid dry ice and shatter the pipes. Next, draw a crossed-out water drop. The incoming gas is saturated with water, which is routed through molecular sieves. Molecular sieves are vessels filled with crystalline materials that trap specific molecules based on size. They reduce the water content to less than 1 part per million. Beside that, note down mercury removal. Even trace amounts of liquid mercury cause severe galvanic corrosion in the aluminum equipment used further down the line. If any of these strict pretreatment steps fail, the gas will cause physical blockages or metallurgical failure long before it ever reaches the cooler. Now draw the third branch, labeled liquefaction. This is where the core thermal transformation happens. We drop the temperature of the purified gas down to -162 degrees Celsius. This schematic shows the pre-cooled mixed refrigerant process. This tall, cylindrical vessel is where the actual thermal transfer takes place. Draw a vertical coil-wound heat exchanger on your branch. Notice the green loop labeled mixed refrigerant. A specialized blend of nitrogen, methane, ethane, and propane is compressed, cooled, and expanded repeatedly to absorb heat from the natural gas. This alternative schematic displays the APNN LNG process. For larger offshore facilities where storing highly flammable propane is too dangerous, engineers use an all-nitrogen recycle process. It relies on a complex series of turbo-expanders to create the necessary refrigeration without the heavy fire risk. Grab your teal marker. Trace the cooling paths on your drawing, mapping them to those refrigerant loops we just saw. Teal will represent all thermal extraction on our map. Draw a fourth branch labeled safety. Sketch a flame icon for traditional hydrocarbon fire risks, and beside it write RPT. RPT stands for Rapid Phase Transition, a physical explosion that occurs if liquid natural gas suddenly contacts warmer water and instantly expands back into a vapor. By forcing this exact temperature drop, the process achieves a 600-to-1 volume reduction. That exact density change is what makes the global export of natural gas physically possible. This table compares different LNG cargo containment systems. Notice how the membrane tank in the first column is designed to react directly to the ship's hull structure. Draw your fifth branch, labeled storage, and sketch a cross-section of the membrane tank. Above your tank, draw a small escaping cloud. Label it BLG for boil-off gas. Even with thick insulation, heat leaks into the tank. About 0.15% of the liquid cargo naturally evaporates back into gas every single day. Draw an arrow from that cloud over to a small generator doodle. To prevent pressure buildup and recover the economic value of that gas, the boil-off is routed directly into the facility's onboard turbines to generate power. Draw your sixth branch for logistics. Sketch out the large carrier ship and the hard loading arms equipped with swivel joints that connect the processing facility to the export tankers. You can see the immense scale of this equipment on the red-hulled Prelude FLNG vessel. From the moment the gas hits -162 degrees, this entire logistical supply chain becomes a race against thermal expansion. Managing that constant heat and leak dictates the viability of the whole operation. Draw the seventh branch, regasification. Sketch an FSRU, a floating storage regasification unit. This is a specialized vessel that uses warmer ambient seawater to gently heat the liquid back into a gas, so it can flow into the local pipeline network. Next, the pricing branch. The global market follows different rules depending on the region. In the US, prices are set at the Henry Hub based on domestic supply and demand. In Asia, the JKM, or Japan-Korea marker, determines spot prices, while other regions rely on long-term contracts linked directly to the price of oil. Finally, draw your last branch, decarbonization. Sketch a pipeline directing carbon dioxide underground. This represents carbon capture and storage, a necessary step to mitigate the emissions from the initial processing. The industry survives by bridging those regional price disparities, but long-term operations require neutralizing the carbon footprint of the liquefaction process itself. Put your pens down and zoom out. Look at the interconnected web of the 10 pillars we just built. In the bottom left corner of your page, write this sequence: C, P, V, S, S, R, P, S, S, D. This mnemonic locks the exact order of the steps into your memory. Review your color coding. The teal markers track the cooling physics. The red highlights the severe hazard points. The orange traces the physical transport lines across the map. You started with a blank piece of paper. Now you hold a tangible, navigable system. You have mapped the exact thermodynamic and economic parameters of the global energy market.